We are in Unit 9. This is Note 6. Today we are looking at what is called L'Hopital's rule. L'Hopital's rule. Let's take a quick look again about where we've been. In Unit 9, we've done a lot of integration. We reviewed all of our previous integration. We learned integration by parts, integration using partial fraction decomposition. We learned how to evaluate integrals with powers of trig functions. And last time we were together, we did integration using trig substitution. Today we're doing L'Hopital's rule, which is not an integration technique. This is a way to evaluate limits. And you might think, why in the world are we doing limits in the middle of this huge integration chapter? And the answer is we need L'Hopital's rule in order to do improper integrals, which we're doing next. All right? So today we're doing limits. And then we'll get back to integrals next. All right. There's also a good reason why I saved this. I could have taught this to you back when we did limits in our first unit. We could have covered it there because we had all of the knowledge then. Another reason I like to save it till now is that it's another refresher on limits. And I usually find students who had a more difficult time with limits in Chapter 1, they have a much easier time after all of our experience with calculus. They have a much easier time with limits at this point. Okay, so it's another way to hit limits as we're preparing for the AP exam. All right. Okay, so let's quickly do a brief little review on limits to refresh our memory. What do we do? What's the first thing we do when we see a limit? First thing you should do is plug in this number. See if you get a number for your answer. So if I plug in 3 for x in my numerator, I'm going to have 2 times 9, so 18. 18 minus 2 is 16. And 3 plus 1 is 4. When I see that this is a number, I put an equal to sign. I do not put an equal to sign before I know that this is a number. All right? So this limit is just 4. What this means is, as x approaches 3, y approaches 4. That's what that means. It does not mean when x equals 3, y equals 4. A limit is not a function value. A limit is what's happening as x approaches this value. Okay? Now, this works great if we get a number here. It does not work so great if we don't get a number there. Let's take a look at this one. Let's take that same function, but this time let's go to -1. In this case, if we plug in -1 for x, we get 2 minus 2, which is 0, and -1 plus 1, which is also 0. That is not a number, so do not put equal to sign. If you put equals, you're saying something that's wrong. And I'm not going to give you credit if you say something that's wrong. All right? So don't put an equal to sign because it's not equal to. This is not a number. This is an indeterminate form. It's one of many indeterminate forms. Some of the indeterminate forms that we know of are 0 over 0, plus and minus infinity over infinity, 0 over infinity, infinity over 0. Those are all indeterminate forms. Okay? Some indeterminate forms that you might not think of. 1 to the infinity, 0 to the infinity, infinity minus infinity. Those are also indeterminate forms that you might not think are indeterminate. You might say, oh, Mrs. Murray, wait a second. 1 to any number is 1. We learned that a long time ago. And my answer to that is yes. If you just have a problem that says, number 17, what is 1 to the infinity? Yes, that is 1. But if you get number 17 and it says the limit as x approaches, I'd have to think up a good problem here, but for the sake of that is not 1 necessarily. Maybe it is 1, but it's not necessarily 1. Okay? I should have said, well, anyway, I could change that to something instead of infinity here. It's not going to infinity. But this is something, remember these indeterminate forms came from a limit. So this is not necessarily 1. That maybe was something going to 1. Going to 1 to the going to infinity is not necessarily 1. It's indeterminate. Same thing here. Going to 0 is different from equals 0. Those are two different things. Remember, approaches 3, approaches 4, not equal to 4, approaches. Okay? The limit is equal to 4. That means that y is approaching 4. So this is something that's approaching 0. The exponent is approaching infinity, not equal. So that's why these are all indeterminate forms. Okay? We're going to get a couple of examples where I'm going to show you that these are not necessarily 1 and 0. All right. So what do we do here then? If it's indeterminate, what do we do? Well, in Unit 1, our Unit 1 process was to try to factor, multiply top and bottom by a conjugate, reduce a complex fraction. We had several techniques to use back in Unit 1. This one is one that I would factor. Take out a 2, and then you'll have 2 times x squared minus 1 over x plus 1. And then we can factor what remains in the top, so x plus 1, x minus 1 over x plus 1. The x plus 1's reduce out, which you can reduce because it's not equal to -1, it's only going to -1. So now this is equal to, because we will get a number, plug in -1, we got -2 times 2 is a -4 over 1, so this is equal to -4. Okay? Now, as it turns out, there's another way we could have done this problem, and that is with L'Hopital's rule. Okay? We will get there. Okay? So, we have another couple of examples here of what we did in the past, what we did back in Unit 1, and it's worthwhile. Let's take a look at this. Okay, as x goes to infinity, so we're plugging in, you can think of plugging in infinity, but really that's impossible. You're plugging in a huge number. As you're plugging in a huge, massive number, this -1 won't matter at all. You can ignore it. As you're plugging in a huge, massive number down here, this +1 won't matter at all. So you're left with 3x squared over 3x squared, which reduces to 3/2. All right? This is another one where we could have used L'Hopital's. Example 4. Limit x goes to 7, square root x plus 2 minus 3 over x minus 7. And I didn't in this previous one, I should have said, as you first just plug in a huge unbounded number, you do get infinity over infinity, right? Which is one of our indeterminate forms. That's why we had to manipulate a bit. Okay, if you just plug in 7 here, you get the square root of 9 minus 3 which is 0, and then we have 0 in the denominator, and that's another indeterminate form, right? So we have to do something. Now this is one that, again, we could use L'Hopital's for, but in Unit 1 we didn't know L'Hopital's, so we would multiply top and bottom by a conjugate. And then we would get limit as x goes to 7 of x plus 2, the middle term zeroes out, minus 9 over x minus 7 times square root x plus 2 plus 3. And back in Unit 1 I said don't multiply through on this piece. Only multiply through your conjugates. Your conjugates, yes, multiply through. Your other one, just leave it separate. This is x minus 7, so this reduces with this x minus 7. Now we can plug in 7. Square root of 9 plus 3 is 6, so we get 1/6, which is a number. So our answer is 1/6. Okay? So all three of these are examples of when we could have used L'Hopital's. Now, but we didn't have to because we had other techniques. So why learn L'Hopital's? Okay, what about this one? Limit as x approaches 0 of sine x over x. If you just plug in 0, sine of 0 is 0. 0 is 0. So we get this indeterminate form. And what would we do to manipulate this? We're not going to multiply by a conjugate. We're not going to factor. What would we do? Use some trig identities, maybe? This is a great one to use L'Hopital's on. All right? So let's state L'Hopital's. L'Hopital is named for a French mathematician, Guillaume L'Hopital. All right? Now the reason that I have two spellings of this up at the very top, there are two spellings of his name. When he was alive, he used this spelling of his name. All right? He lived back in, he lived back in the late 1600s. All right? And when he was alive, he used this spelling. But sometime since the late 1600s, the French language changed their spelling of this. And I don't know anything about French. This is what I have read. They changed the spelling of this OS to an O with this symbol on top. All right. So when I was in calculus learning this, the textbooks all had this spelling of his name. Okay, it is pronounced L'Hopital. Regardless of how you spell it, it's pronounced L'Hopital. All right? But this is the way I learned it, and so it's the way I kind of revert back to. If I'm just writing it quickly, this is how I'm going to write it because it's how I learned it. But nowadays, textbooks are using the way they want to spell it, the way he spelled it. Which that's great. I like it. So I'm trying to convert. It's just when I get in a hurry, I'll always go back to that. Okay? You can choose whichever one you want. All right? And you're not going to be graded on the spelling, so just go ahead and give it a shot. All right? Okay. L'Hopital's rule. L'Hopital's rule says this. If the limit as x approaches a of f of x over g of x. Okay? It has to be a fraction. It has to be a function over a function. All right? If this limit results in the indeterminate form (0 over 0) or plus or minus infinity over infinity. Only those indeterminate forms if this limit results in one of those indeterminate forms, then here it comes, the big one, drum roll. The limit as x approaches a of the f of x over g of x, I know you can't wait to see this, is equal to the limit as x approaches a of f prime over g prime. That's it. Okay? F prime over g prime. Couple things. This is not the quotient rule. We're not taking the derivative of f over g. We're taking the derivative of f and dividing it by the derivative of g. Okay? So get it right. Okay? So let's take a look at this problem that we just were looking at here. We were looking at this limit as x approaches 0 of sine x over x. And we got this indeterminate form, didn't we? So here's what I would say. I would say, okay, I get 0 over 0, which is a L'Hopital's indeterminate form. So then I would say, okay, that means that this limit is equal to the limit as x approaches 0 of the derivative of the top. The derivative of the top is cosine x over the derivative of the bottom, 1. Now plug in 0. Cosine of 0 is 1. 1 is 1. So this is equal to just 1. Now you'll notice something that I do in all of my problems. When I do apply L'Hopital's, I'll put a little LH. You do not have to do that. I like to do that to show how I got from this step to this step. Because right now they look very different, right? And if you didn't have that, when you're looking back at your notes and stuff, you might say, wait a second, what in the world happened here? So this tells you, oh, L'Hopital's, that's what happened there, okay? Now one more thing. This is great for Mrs. Murray. This is great work to show for Mrs. Murray. For me. For my test, for my homeworks and stuff, and quizzes, this is great to show for Mrs. Murray. This is not enough to show for AP. So if this was an FRQ on AP, then they need to see two things. They need to see the limit as x approaches 0 of the top, and they need to see the limit as x approaches 0 of the bottom. They need you to say what each of those is. In this case, they're both 0. They need to see that. You can say this too if you want, but they need to see this. Otherwise, you will not get credit for applying L'Hopital's correctly. All right? So just give it to them if you're on a FRQ AP exam. Okay? Let's look at another example. What number are we on? Number 6. Oops, let me pull this down a little bit. Okay. The limit as x approaches infinity of that's negative infinity of x squared over e to the negative x. Okay. Well, first of all, we think of plugging in a huge unbounded negative number. So this numerator will be going to infinity. You can even say going to infinity. All right. The bottom is going to, what's the bottom going to? E to the negative of negative, right? Infinity. So what is that? That is infinity, right? Notice I did not put an equal to sign. If I did that, I've said something wrong. This is not wrong, it's just sitting out there. Right now, by itself, it doesn't have a whole lot of meaning, but it's not wrong. So, but if I put an equal to sign, it would be wrong, because this limit is not equal to infinity over infinity. It's not. So don't put an equal to sign there, all right? Okay, but this infinity over infinity is one of our L'Hopital's indeterminate forms, right? So I can come off to the side and do L'Hopital's rule. So this is equal to that same limit of derivative of the top, 2x, over derivative of the bottom, negative e to the negative x. Now plug in again. The numerator will have a negative unbounded number. The denominator will be a negative, again, unbounded number. This is infinity over infinity, which is another L'Hopital's. So we'll come over and do L'Hopital's again. Limit x goes to negative infinity. Derivative of the top is 2. Derivative of the bottom is e to the negative x. Time to plug in again. 2 is on top. What's on the bottom? Infinity, right? What does 2 over infinity go to? 2 divided by a huge unbounded number goes to 0. That goes to 0. So this whole thing is 0. Okay? All right, number 7. I'm going to fix my power. Okay. All right, number 7. We have the limit as x approaches infinity, positive infinity this time, 1 over x ln of x squared. Okay. Let's start by plugging in this unbounded number. 1 over an unbounded number is 0. Natural log of an unbounded number is infinity. Remember the graph of natural log does this? It does go to infinity, just really, really slowly. Really, really, really slowly. But it'll get there. Eventually, it gets there. Just takes its time getting there. Okay? All right. So we have 0 times infinity. That is indeterminate. But it's not L'Hopital's. It's not L'Hopital's. So we have to make this into a fractional form so that we can apply L'Hopital's rule. So make this into a fractional form. Well, this one's not too hard to make into a fraction. I've made it into a fraction. Now before I do anything with it, this 2 on the x squared, I can make my life a little bit easier. If I bring that 2, I'm going to apply the log property where I can bring the 2 to the front, right? And if I bring this 2 to the front, I might as well, since now it's 2 times the whole thing, I can take it out of the entire limit and make my life really easy. So this is going to be just 2 times the limit as x goes to infinity of ln x over x. Let's plug in a huge unbounded number. The numerator is infinity, the denominator is infinity, and now we have L'Hopital's. So by making this into a fraction, we were able to use L'Hopital's. So I'm going to apply L'Hopital's, and I get 2 limit as x goes to infinity of the derivative of ln x is 1 over x, the derivative of x is 1. Now let's let x go to infinity. X goes to infinity, this piece right here goes to 0, and so we have something going to 0 divided by 1. This is just 0. So this limit is 0. This time, infinity times 0, I'm sorry, 0 times infinity was 0. But it's not like that all the time. Okay? I will tell you that this time it worked out that way because ln is a very, very weak infinity. It's a very weak infinity. But I could do another one where it wasn't weak. In fact, we have time. Let's go do one real quick. What about this? What about this? If I just plug in infinity, I get infinity over infinity. That's L'Hopital's. So use L'Hopital's. What's the derivative of e to the x? E to the x. Derivative of x cubed, 3x squared. Plug in infinity. Another L'Hopital's. Derivative of e to the x. Derivative of 3x squared. Plug in infinity. Infinity over infinity. Another L'Hopital's. What's going to happen here? We finally get down to e to the x over 6. Plug in infinity. We get infinity divided by 6. That's infinity. Infinity is a much stronger, e to the x is a much stronger infinity. Think of the graph of e to the x. It went to infinity super fast. Okay? Much faster than slow going, take your time, ln x, right? So, this is a much more powerful numerator than this is. We will talk more about that in our series unit. So we will get there. Okay, number 8. Number 8. Doing good. Limit as x approaches 1 from the positive side of 1 divided by ln x minus 1 divided by x minus 1. Oops, let me get back on the screen here. Okay. Plug in 1 from the right. That's like 1.000001. This is going to be, the denominator is going to be 0 but positive. So this whole thing is going to infinity. This denominator is also going to 0 but positive. So this whole thing is also going to infinity. Infinity over minus infinity, it sure does look like 0, but it's not necessarily 0. Maybe it is, maybe it's not. We just don't know until we figure it out. This is indeterminate, but not L'Hopital's. Okay? So we have to force this to be a fraction so that we can use L'Hopital's on it. So let's force it to be a fraction by adding fractions. How do we add these two fractions? We get a common denominator. That's how you add fractions. So this will be x minus 1 minus ln x all over ln x times x minus 1. And now I don't need those outer parentheses. Okay, let's plug in 1 from the right again. This is going to be 1 minus 1 is 0 minus 0, so 0 on top. 0 times 0 is 0. So now it's indeterminate and it's L'Hopital's indeterminate form. So now we get to apply L'Hopital's carefully. Okay, derivative of the top. 1, the derivative of x is 1. The derivative of negative 1 is 0. The derivative of ln x is 1 over x. Now in the bottom we need to be careful because we have to use the product rule. This is a product, right? Product rule. So the derivative of ln x is 1 over x. The derivative of x minus 1 is 1. Okay. I want to clean this up a little bit. I'm going to multiply top and bottom by an x just to clean it up. All right. If I do that, I'm going to get x minus 1 over x minus 1 plus x log x. Okay. Plug in 1 again. The numerator, we're going to have a 0. The denominator, we're going to have 0 plus 1 times 0. So we get 0 again, and so we need L'Hopital's again. So L'Hopital's derivative of the top is just 1. Derivative of the bottom is 1 minus 0, and now we need to use the product rule again here, right? So 1 times ln x plus x times 1 over x, and now this is just a 1, right? So when I plug in 1 this time, I get 1 on top. On the bottom, I get 1 plus 0 plus 1, which is 2. So this is a half. So this time, infinity minus infinity was a half. You just never know. You just never know. Example 9. The limit as x approaches infinity of 1 plus 1 over x all to the x. Okay. All right, let's plug in this huge unbounded number. If we do that, we're going to get 1 plus 0, because this little piece here, 1 over something going to infinity is 0. So this is going to 1. The exponent is going to infinity. So this is going to 1 to the infinity. This is an indeterminate form. Again, if we just had the problem, what is 1 to the infinity? You would say 1, and you would be right. This is not exactly 1 to the infinity. This is something going to 1, to a power that's going to infinity. That's why it's indeterminate. All right? Maybe our answer is 1, or maybe it's something else. We're going to find out. Okay, this is a little bit of a challenge though, because how do we get this in fraction form? We need to get it into something that we can use L'Hopital's for. So we need to get this in fraction form. But how? Well, we're going to use something, you're going to think that this is a trick, but it really is not a trick. This is a technique. And we need to involve logs. Why do I want to involve logs? Because look, I have an x in the exponent. I have an x in the exponent, don't I? I need a way to pull that x down to make it a coefficient. That sounds like that log property, but right now we don't have any logs involved. So I need to somehow get logs involved. So here's what I'm going to do. I'm going to let y equal my limit. Let y equal my limit. Now I can come in and take the log of both sides. I can't just take the log of this, because that would change the value of it. But I can set some letter. It doesn't have to be y. It can be any letter I want, except for x. I can set a letter equal to that, and then I can take the log of both sides. Okay? So I have the natural log of y is equal to the natural log of this limit. Okay? Now, there's a property of limits that you don't know until now, but the natural log of a limit is the same as the limit of the natural log of that function. So in essence, I can switch the natural log and the limit. It's a property of limits and logs together. All right? Now I'm where I want, because now I can pull this x to the front of the natural log, right? So I'll have limit as x goes to infinity of x ln 1 plus 1 over x. I'm almost there, but I still don't have a fraction. I still need a fraction after this limit. I'm almost there. I just need to force this x to go to the bottom as a 1 over x. Okay? So I will have the natural log of y is equal to the limit as x approaches infinity of ln of 1 plus 1 over x divided by 1 over x. I finally did the work to get this to be a fraction. Now let's hope that we can apply L'Hopital's. Let's plug in infinity. Now when we plug in infinity, we get natural log of 1 plus 0, so natural log of 1. That's 0. Plug in infinity down here, 1 over infinity is going to 0. So yay, we get to apply L'Hopital's. All right, we're applying L'Hopital's. Okay, limit as x goes to infinity of, all right, I need the derivative of natural log of 1 plus 1 over x. So the derivative of ln of u is u prime over u, right? So I need the derivative of this over itself. So this is going to be a complex fraction just in the numerator. So this will be the derivative of this. The derivative of 1 is 0. The derivative of 1 over x is negative 1 over x squared. So that's the derivative, and now this is the u part. So that's u prime over u divided by the derivative of 1 over x, which is negative 1 over x squared. This looks like a mess, doesn't it? Let's clean it up. Let's clean it up. Okay, so I think what I'm going to do is I'm going to multiply top and bottom by a negative x squared. Top and bottom by a negative x squared, like that. And if I do, then on the bottom I just have a 1, right? On top, I can multiply negative 1 over x squared times negative x squared, and I just get a 1. And so I'll have a 1 over 1 plus 1 over x. Okay? Now let's let x go to infinity. This piece is 1, so we have 1 over 1 plus 0. I'm sorry, this piece is 0. As x goes to infinity, this piece is 0. So I have 1 over 1 plus 0, so that's 1. So I have natural log of y is equal to 1. So remember, y was equal to this limit. This limit is y. We didn't find y yet. We found the natural log of y. So how do we get y? E to both sides. So we found out that the limit as x approaches infinity of 1 plus 1 over x to the x is equal to e. If you look back at your formula sheet, the very first thing on there is this. It's the definition of E. All right? This is our definition of E. And we just proved it. So that's pretty awesome. Pretty awesome. So now that you know and you know where it came from and it's on your formula sheet, now I need you to recognize this guy. I need you to recognize that guy. You're going to need it when we do series. All right? You're going to need that when we do series. So I will remind you back then. But I have one more example for you. One more example. Number 10. The limit as x approaches infinity of 1 plus 5 over x all to the x. Okay, let's see what this is. So this is another one. When you plug in infinity, you're going to get 1 plus 0, so 1 to the infinity, indeterminate but not L'Hopital's, so we have to force this to be a fraction. The only way to pull down this x is to involve natural logs. So I'm going to make it so that I can do natural logs by setting y equals to that. And then I'm going to take the natural log of both sides. Okay? So I'm going to have the natural log of y is equal to, I'm going to go ahead and switch these two. So the limit as x goes to infinity of the natural log of 1 plus 5 over x, okay, it would be to the x, but we want to pull it down, right? We want to pull the x down, but we don't even want to, we do want to pull it down, but then we really want it to be under here. So is this okay? Can I do that? It just saves us about 3 steps if I do that. Now I plug in infinity again, and I have natural log of 1 over 1 over infinity. That's L'Hopital's. So now I can apply L'Hopital's. And we're going to get a big complex fraction here, so don't be scared. That's a big complex fraction. So the derivative of ln of u is u prime over u. So the derivative of this piece, the derivative of the argument, is 0 plus the derivative of 5 over x. So that's going to be negative 5 over x squared. All over u, which is 1 plus 5 over x. That's just the derivative of the top. Now I need the derivative of the bottom. Negative 1 over x squared. Let's clean this up by multiplying by negative x squared over negative x squared. Okay, so we'll have natural log y is equal to the limit as x goes to infinity of, okay, the x squareds cancel here, the negative cancels, we're left with 5 over 1 plus 5 over x all over 1, right? Now let x go to infinity. This piece is going to 0. This piece right here is going to 0. So we have 5 over 1. So this ln of y is just 5. So e to both sides. So we showed that the limit as x goes to infinity of 1 plus 5 over x to the x is e to the 5th. Just now in example 9, we showed this. So what do you think this would be? This would be e to the 7th. So the limit as x approaches infinity of 1 plus a over x to the x is equal to e to the x. Now if you know this, then you don't have to show this if it's a multiple choice question. If it is a multiple choice question, show me your work. I'm sorry, if it is an FRQ question, then show me your work. All right. Okay, one more thing before I go. It's good to know this. and I have it on your notes, but in case you don't have the notes in front of you, L'Hopital, I have this little, I like to put a little history note when I can. L'Hopital's rule first appeared in a calculus textbook in 1696, and that was by L'Hopital, and it was credited to him. However, it was actually developed by one of the Bernoulli brothers, Johann, who sold the rights to L'Hopital to make some money. Okay? Sort of thing happened a lot. And FYI, Bernoulli studied under Leibniz and sided with him over the big Newton-Leibniz debate over who founded calculus. Okay? All right. So a lot of stuff went on back in this time. A lot of the development, a lot of the things we still use. Okay? Anyway, interesting. All right. Go practice L'Hopitals, and I think that you'll like it as much as I do.